Hello, this is Math 2270 coming to you from the College of DuPage for summer 2020, and this lecture is entitled First Order Linear Differential Equations Concluded. Here's a problem. You know what to do. Let's see how you did. Well, first thing is, and that's why we had this constraint here because the cosine of x is never 0 there, we divide all the way through by cosine x, getting this on both sides. And then we realize that this is the tangent of x, and this is the secant. Now, you have some choices here about how you handle that. This is the way I handled it. And so now you see you have this in the form of y prime plus p of x times y equals some other business over here. And so that means that this is p of x. So if you integrate the tangent, you might get this expression. What I'm going to do is I'm going to put that minus 1 up here. And the secant, the absolute value of secant is always greater than or equal to 1. And so that's going to be the ln, the absolute value of the secant is what I get for that. So that means our integrating factor then is e to this integral, and e to the ln absolute value of secant x is equal to e to the ln secant x. I can drop the absolute value because of this interval up here, and those are inverse functions to each other, so that is just secant of x. So now I'm going to multiply all the way through our differential equation right here, both sides by our integrating factor, which is secant of x. So we do that here. And then, and you should check, let's check maybe one time, you see this is, in fact, secant times y prime plus secant times tangent, which is the derivative of secant times y prime. So this is indeed the secant of x times y, derivative of that whole thing. So I just checked my work is equal to this. So now we're going to integrate both sides. Now, when I integrate this side, I'm clearly just going to get this. When I integrate the other side, I have some options. You could approach this different ways. There's different trig identities, and so on and so forth. I elected to make this integral simpler by calling this sine of 2x. So this 2 cosine x, sine x is sine of 2x, so I get that. And I then do the integrals, and I get this. And then I'm going to divide all the way through by the secant of x. Now, 1 over the secant of x is the cosine of x. So I'm really, could think about that as multiplying all the way through by the cosine of x, and I get this expression. Notice I put my c here. And I do have an initial condition. And then I can simplify that a little bit because cosine times tangent is minus sine. And then I plug in my initial condition up here. I get c is 7, so there is our solution. Here's another problem. You know what to do. Okay, so we divide all the way through by t to get it into this form. Our integrating factor is going to be mu of t is this. I can take that 2 and put it up here because of properties of logarithms, and I can call that the absolute value of t squared or t squared. So I multiply all the way through by t squared, this equation right here. And I should get this. You should check this. I'm skipping that step for right now, but you can see that I took t squared times the right-hand side to get this. So now we're going to integrate both sides. So when we integrate both sides, what will happen is this is what we find. And I simplify that just a bit because I'm dividing. Then I can divide both sides by t squared to get this. So now I've solved for y of t. I can substitute my initial condition. C is 1 over 12, and there is my answer. Here's another problem. You know what to do. Those of you who are paying attention are saying, oh my gosh, there might be some integration by parts happening here. I think you're right. Let's see how you did. So we divide all the way through by this initial t, getting this. And now we could get the integrating factor. Now this is really important that you realize that that formula was y prime plus p of x. So you see p of x is actually minus 2 over t. This is really important because this will take you down a whole nother rabbit hole if you screw that up. So that is what p of x is. So my integrating factor, there's a minus sign there. It's a little bit hard to see. Here it shows up clearer. I get this. Again, I'm going to move that minus 2 up here, and that's going to be the same thing as t to the minus 2. And I'm not showing you this, but if I then multiply all the way through this equation right here, the changed equation, by my integrating factor, I do get this expression. So now what I'm going to do is integrate both sides. So I will get this is equal to this. Now you see that this is integration by parts. Yes, we will be integration by parts, and so you have to make sure that you understand where all of that came from. You should check and make sure that you can do this. But we get this is equal to that after we integrate by parts. And then we multiply all the way through by t squared to get this as our solution, but there's a c. So we plug in the initial condition to find out what c is. And we find out that c is pi minus 1 over 4. And then we can plug that into the answer right here, and we have the problem completely solved. Here we're to find the behavior of the following IVP as t tends to infinity. A lot of times this is a question that asks in differential equations course. And so and if this behavior depends on the value of y0, we're just saying that's a general number. It is a number, but it's a general number. I'll talk about the dependence. You know what to do. Let's see how you did. Okay, so you reorganize this into our form, but notice now that p in this case is minus 1/2. Your integrating factor then is going to be this. I'm skipping a step here, but you should confirm that. I did check it. And this is what we have when we multiply all the way through by the integrating factor, and is equal to that. So now we're going to integrate both sides. We'll get this on the left-hand side. And here we have integration by parts again. You should go through and actually do that integration by parts. I just threw a c out here to start with. And so this is what you get when you integrate by parts. You should make sure that you do get that. And that means that y is equal to, now I'm going to multiply all the way through by e to the t over 2. And I will get this. Now notice I have a term then that does have an exponentials, and these guys ends up canceling out. Then I use my initial condition, y0, and I find that y0 is this, and that means that this constant that I have over here is this. Now, I can look at this and I can see that, yeah, these are just nice trig functions added together, but this is an exponential function, so this will go to minus infinity if c is negative, and it will go to positive infinity if c is positive. And if c is 0, that term will just drop out, so you have a nice finite condition. So you see what happens is, and if you think about that, the range of values then is this 24 over 37 minus 24 over 37 is an important thing because it wildly changes the nature of the solution. So that's what is happening here. Now, there is a major takeaway from this example. IVPs can be extremely sensitive to the initial conditions. This was observed first by Poincaré and more famously and way later by Forrester, an MIT meteorologist. It is essentially the foundation for what people call chaos theory. Now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. Take care of yourself and of each other.